Mapping with UAV is a booming in the space of geospatial data collection using drone. One can carry out topographic surveying with highly accurate and non-compensable quality of traditional surveying methods. The primary advantage of drone surveys include less time consumption, cost effectiveness, reduced usage of manpower that can efficiently work in atmospheric conditions. Therefore, UAV mapping is now a common tool across many applications with different deployment and accuracy demands. So in today's presentation, I really want to show you some of core background principles and key steps behind all of the data processing that you got from a UAV survey in order to obtain precise 3D information. The overview of the presentation is briefly I touch upon the basic themes of photogrammetry and UAV, such as platform, payloads, system component, etc., and then focus on data acquisition process and photogrammetric process. Of course, further we can talk how to increase the accuracy of any drone survey at the end of the presentations. Okay, so right, and let me start with the definition that is UAV, that is unmanned aerial vehicle. The term UAV commonly referred to as a drone, as you all know that one. It can be defined as a generic aircraft designed to operate with no human pilot on board. So they may be a remote control, semi-autonomous, autonomous, or have a combination of these capabilities. So UAV is a simple term that is more commonly used in computer science, robotics, artificial intelligence, as well as in remote sensing and photogrammetry communities. As a fast-growing market with numerous daily new opportunities, several names are currently used by people involved in this booming aeronautical sector to label this unmanned aerial system found in more and more areas. Here you can see an overview of the correct terms that were adopted by the major professional actors of the UAV domain. The first name, RPV, which is called remotely piloted vehicle. So when it is remotely controlled from ground, this name is normally used. This system requires reliable wireless communications for control. Additional term like RPA, which means remotely piloted aircraft, ROA, remotely operated aircraft, or we can see RCH, it means remotely controlled helicopter, or final one is MAV. So that is micro aerial vehicles. We can also found these names in this drone domain. Okay. The other popular term in this domain is the UAS. So that is unmanned aircraft system. The term UAV is used to describe the aircraft itself, whereas the term UAS is generally used to describe the entire operating equipment, including the aircraft. It consists of not only the UAV, but also the pilot, the person who operates the UAV, and the system which connect the platform and the operator. So that is ground control stations, including the communication subsystem and the wireless data link. So a UAV means a complete solution, including platform, payload, software, operator, ground control station, radio controller, and all the things that we need to do our project or our survey. Okay. Additionally, terms like RPAS, so that is remotely piloted aircraft system, is used when it is operated remotely from the ground. Also, we can see the name is small unmanned aircraft system if the aircraft weight is less than 25 kg. The flight of UAVs may operate with various degree of autonomy, either under remote control by a human operator or autonomously by onboard computers. Okay, so uh, then let's talk about the different type of UAVs or platform. So drone actually can be classified on a different basis, say based on usage, like drone photography, drone mapping, and drone surveillance. According to the weight, UAVs can also be categorized into 5 groups, such as nano, micro, small, medium, and also large. Okay, so you can see in this table the weight of each type of drone, how it changed, and how they are normal operating altitudes is changed, and mission radius and endurance and payload and etc. Okay. However, the best classifications of drones can be made on the basis of aerial platform. Based on the type aerial platform used, there are 4 major types of drones. The first one over here is the multi-rotor drones, sometimes we call as rotary wing drones. It uses 2 or more rotating blades that revolve around fixed mass to generate the lift. It take off vertically and land vertically, so you don't need big runway for landing or take off this type of drones. So they give use such great control over positions, and they are perfect for aerial photography work. Okay, so you can see here there are 3 types of rotary drones: tricopter, hexacopter, or quadcopter. So because they have a number of copter, based on that we can also categorize as these based on these names. Okay. But downside of multicopter is limited endurance and speed, making them unsuitable for large-scale aerial mapping, long endurance monitoring, and also long-distance inspections such as pipeline, road, and power line. Also, they are very inefficient and require a lot of energy. So they are basically limited to around 20-30 minutes when carrying a lightweight camera payload. But latest battery technology actually bring them into 45 or 1 hour maximum. Actually, it is a maximum. Therefore, multi-rotor drones are very good platform for mapping small areas or obtaining 3D imagery of a single object in a single flight. Okay. Okay. The second one is the fixed wing drones, as opposed to rotary wing, that is actual helicopters. You can see one picture is here. They use a wing like a normal aeroplane to provide the lift rather than vertical lift rotors. Because of this, they only need to use energy to move forward, not hold themselves up in the air. So these drones are much more energy efficient compared with the rotary wing drones. Due to their increased flight duration and efficiency, they are able to cover long the distances, map much large areas, and loiter for long time monitoring their point of interest. Okay, but a bad thing of a fixed wing aircraft is obviously their inability to hover in one spot. You need a huge open area for takeoff and landing too. So it is very difficult to find such kind of area, especially in urban areas. So that is the major problem of fixed wing drones. Okay, while a multiple rotor has many different rotor to hold it up, a single rotor has just one. Okay, so you can see the next type of drone, that is a single rotor drone. So it has one rotor plus tail rotor to control its heading. Helicopters are very popular in manned aviation, but currently only fill a small niche in the drone world. A single rotor helicopter has the benefit of much greater efficiency over multi-rotor. This is why actually a quadcopter is more efficient than an octocopter. Okay, if you need to with the heavy payload, for example, aerial lidar laser scanner, or have a mixture of holding with long endurance or fast forward flight, then a single rotor helicopter is really your best bet. Okay, but the downside are their complexity, cost, and also their vibrations. Okay. So that's why actually it is not normally used in the survey domain. The last one is the fixed wing hybrid VTOL drone. Actually, now now you can see rotary wings and also fixed wing. These two type of drone have plus minus things. So if you put these two together into a third type of drone, sure, it will be the best drone price. Okay, so they fly like a plane into the mission, so very energy efficient. So you can fly hours and hours based on this drone. Thus, this become a very popular now. But due to the when compared with the rotary wing, this is quite the high cost instrument, and also not yet it's not normally used in some of the application areas. Okay, still we can see this type of drone used in some application yet. Okay, so the next topic is the payloads. So what is payload? The payload is the equipment the air vehicle carries to perform its duties. The payload is the weight a drone or UAV can carry. There are a number of different payloads available with numerous different uses and capabilities. It is usually counted outside of the weight of the drone itself and include anything additional to the drone, such as extra cameras, radar, laser scanner, sensor sticking on a GPS system, communication technology, and packages for delivery or more. So the drone payload varies depending on the objective of your missions. For example, if you were using a drone to deliver medical supplies, then your payload might be life-saving vaccine or first aid kit. If your objective was to survey a remote plot of land for research, then your payload could be a high-powered camera. Very large UAVs used in the military have much large payload than the popular drone. So you can see some of the example here. In most of the survey, we can use camera sensors. It based on your application, you can attach an integrated RGB camera, thermal camera, the high sound camera, or multispectral camera. Not only then, based on the objective, also you can attach maybe LiDAR sensor or gas detector. As I said, maybe you can deliver some packages. So whatever thing carry with your UAV system, we call as payloads. Okay. Okay, and now let's see a system component of any drone system. As you can see here, this figure demonstrates a high-level architecture of a UAV system and its main components. The main component of a UAV can be divided actually into three main categories. The aerial platform, which include the airframes, a precise navigation system, flight controller, the power system, the payload, and a sense and avoid system. The second type of component or major group is the ground control station, which allows the human control from remote emplacement. Then the third group is the communication system, which support the communication between the other two components. Okay, who is the controlling this aircraft? Actually, the aircraft is controlling by the flight controller. The flight controller is the central processing unit of a drone. Flight controller can be stabilized the drone also. The flight controller can have multiple sensors integrated on board or communicate with the external sensor unit. So you can see here, so there are some of the UAV system sensor include with this system. Why do you need these additional sensors? For example, if you want to do the navigation and put into advanced measures, you need to have some additional sensors like this. For example, you need to have a GPS interface to the flight controller, and you need to have a compass interface to the flight controller. Because compass help the flight controller to change the heading and direction, GPS will let the flight controller to know the position. Okay, and also if you want to detect the altitude when you do the landing and takeoff, so you can have a sonar. Further to that, let's see, if you want to control the drone, you need to have a RF receiver attached to the flight controller. Many more things that you can include as a system sensors. Flight controller reads the data provided by the sensors and processes it into useful information, and according to the type of control, either transmit this information to the ground control station. So the flight controller implements the communication interface with the ground control station. More precisely, commands from the ground control station are processed by the flight controller. Okay, so the next thing is the ground control station. A ground control station is an on-land facility that provides and capabilities for human operators to control and or monitor UAVs during their operation. Ground control station vary in size according to the type and mission of the drone of a drone. A ground control station communicate with the drone through the wireless link to send commands and receive real-time data, thus creating a virtual cockpit between these two systems. Okay, so the last system is the system component is the data links. As I said earlier, the data link refers to the wireless link used to carry control information between the drone and the ground control station. The adopted communication link depends on the UAV operation range. Okay. Okay. Right. Now, let me talk a little bit about the growth of commercial drone market according to the current applications. Drones are used for multiple applications ranging from filmmaking to emergency response. Professional use of drones is also growing. So if you look up at the application here, where the drones are and what are the major applications, you can see clearly that aerial photography and video service providers face a crowded market space. They are used, you can see 38% of drones are used for aerial photography and or video photography. Of course, it is true, and you have seen it in also in Sri Lanka as an example. Platinum Pro is used by many people for taking aerial photography or making video photography. Okay, while dozens of other industries use drone, the next fast growing commercial adopter is the survey industry. For surveying, mapping, and GIS, it's almost around 17%. That is the state of art for surveying industry today. Additionally, these services are high demanded in the real estate and construction sector owing to their ability to survey lands, provide continuous and precise project notifications, improve safety, and prevent dangerous incidents on construction site, and many more things. So you can see also it show 88% usage. and 7% usage respectively. The other thing is agriculture. It is almost similar to the construction area. It is 7% when compared with the other application areas. So these are 5 main application areas that use a drone. So other application, actually, we are not considering this small application. So they are the 5 main application area where drone are used. Okay. So it is very important to know the way how to use this technology correctly to obtain good output. Okay. So why is there is a sudden massive interest in drone mapping? There are various benefits of using drone in 3D mapping when compared with traditional surveying method. So what are the benefits? The first one, faster data acquisition, reduced field time. Capturing topographic data with a drone is up to 5 times faster than with land-based method and require less manpower also. With advanced technology, something like PPK geotagging, you also save time as placing numerous ground control points is no longer necessary. The second benefit, it is reduce the survey cost. The cost of drone survey are often considerably lower, so you ultimately deliver your survey result faster and at a lower cost. The next one, it provides accurate and various output at one go. Total station, only measure individual points. One drone flight produces 1,000 of measurements, which can be represented in different formats. So what kind of deliverables can you expect with drone surveying? It depends on the camera or sensor and the software you are using for post-processing. RGB mapping camera together with most photogrammetric software can produce AutomoSAG map, point cloud, digital surface model, digital terrain model, contour maps, 3D model, and etc. So how accurate is a drone survey then? The performance and type of drone, the quality of its component, the camera resolution, the height at which the drone fly, the vegetation and the method used to geolocate the area images can heavily influence the accuracy of drone survey mapping. At this point, actually, it is possible to reach an absolute accuracy down to 1 centimeter and also 0.7 centimeter ground sample distance under optimal condition with the high-end surveying drone. Okay. So the next benefit is we can map in accessible area. So a survey of inaccessible location is another benefit. An aerial mapping drone can take off and fly almost anywhere. You are no longer limited by unreachable areas, unsafe steep slope, or harsh terrain unsuitable for traditional measuring tools. You do not need to cross down highways or train track. In fact, you can capture data during operation without an organizational overhead. Not only that, flying at low height, drone create a very sharp image and a clear overview which can be used to actively monitor and inspect activity, infrastructure, and building on the surface. Further, compared manned helicopters and planes, drone can get much closer to the survey goal, resulting in higher data density, resolutions, and overall survey quality. Drone also provides ability to operate in hostile environments such as smoke, ash, volcano, and etc. Because of these benefits, drone is very popular in survey domains. Right. Now I will explain some of core background principle behind all of the data acquisition and data processing step. Then we can talk a key step and their concept also. Okay, so then what is a drone survey? Actually, a drone survey refers to the use of a drone or unmanned aerial vehicle to capture aerial data with downward facing sensors. That's all. Then these photos are processed to generate georeference orthomosaic elevation or 3D models. Okay, right. Now we can talk how to use this UAV for 3D mapping. It consists of three major steps. The first one is the mission planning. The next one is the data collection process. And the third step is the data processing. The last two things actually they are not compulsory things. They are additional step. If you are interested to have line work or that meaning vector data outputs, then you can use last two steps in order to obtain vector data. Okay. Photogrammetry is the main method that used to obtain 3D information from 2D images. As such, photogrammetry is mainly used during data processing of drawn images, and you can get all of these nice product based on these input data. So what are they actually? You can obtain orthomosaic maps, NDV maps, a point cloud, digital terrain model, digital surface model, texture 3D models, and many more things. Okay. Okay. As I said, everything we need from UAV data comes from concept of photogrammetry. So here I expect you to give a minimum basis understanding on photogrammetry first. What basically is the photogrammetry? What are the basic requirements for photogrammetry? I briefly touch upon the basis and other thing on photogrammetry, and I hope somebody is listening to the photogrammetry first time here. I hope. Okay. Photogrammetry in the general sense is the art and science of making measurement for photographs, especially for recovering the extract position of surface points. Briefly, we can say the photogrammetry is creating 3D data from 2D photographs. The output of this step is a rich 3D model. So this is the ultimate aim of the photogrammetry. What is the principle of photogrammetry then? First, I will tell what is meaning of a photograph. A photograph is a perspective projection of 3D objects into a 2D plane. You can see in this picture. So this is a 3D scene. So you can see this is the photographs or image. So image means if you convert this 3D scene into 2D by projecting all information into this 2D plane, we call this as a photographs. Okay, photograph is a 2D projection of a 3D scene. How to project this 3D information into this 2D plane? So it based on the perspective projection. Perspective projection means actually each and every ground point should be projected to this 2D image plane passing to the one common point. So this is the center of the camera, Okay. So based on this concept, we can obtain a 2D image. Okay. So take all the object points, and this object point you can project it to 2D plane, and then we can obtain a photograph. So this process we call as a photography. The reduction of a 3D object into a 2D image implies a loss of information, primarily the depth. Okay, so you know when convert 3D into 2D, you will lose some information. It is basically depth information. So you don't have now depth information of these position. Okay, only 2D information, XY coordinate. You know the position, but you don't know the distance to that point from your locations. Okay, and yeah, then photogrammetry, the reverse process of the photography process. So that means we want to convert this. So you want to convert this photograph into real world again. So this is the reverse process of photography. Okay, so it converts 2D photograph back into the real 3D scenes. Okay, we can consider an image point in a camera image. So this is the one example. This image point define a ray based on the image point and camera location. We can generate a line. So we know that object point related to this image point should be located along this line. Okay, but we don't know where is this one because we don't have depth information or height information, because of we don't know where is that point located with along this line, but you know it should be along this line. Okay, so we can generate a line based on the point, image point, and camera location. We can generate, and we want to know the correct location of the object. Okay. Okay, why we can't get the exact location based on this image? Because object areas cannot be reconstructed completely with just one photograph due to the loss of information within the object are converted into the photographs. So that is the reason. Okay. Okay, now let's see if you can take a photograph from this camera location, and also, you can take a photograph from this camera location, and also you can take the another photograph from another camera location, but covering the same object area. Okay, so you can see here as an example. We have two photographs taken from two different camera locations, but considered in the same object area. So same information you can see in both photographs. Okay, now I can select one image point from first photograph. So this is my image point. And if you go to the second photograph, I can see the same points. So this one is the point related to this image point. Okay, by knowing your camera location and image point, you can generate this array or this line. And same thing you can do for the second photograph. By knowing the image point and the camera location, you can generate this line. Okay, so by intersecting these two lines, we call triangulating these two lines, we can get intersected point. So we call this is the object point. Okay. By intersecting these two lines, we can obtain actual 3D location of that image point. So that is the concept of the photogrammetry. Okay, so multiple observation from different direction allows for estimating the 3D location of point via triangulation. Triangulation is the basic photogrammetric principle used to reconstruct 3D object. Where intersecting bundle of rays in space are used to estimate the location of a point in 3D. So I use two photographs to explain this concept. But if you have more than two photographs, then you can generate bundle of the rays in order to obtain these 3D locations. Okay. Okay, so then what does meaning UAV photogrammetry? Actually, it is almost same. The principle is almost same in UAV photogrammetry, but the UAV photogrammetry uses unmanned aerial vehicle to take photograph for use in photogrammetry of making measurement from photograph. Okay, uh, the way how collect is changed, but the collection process and thing to consider almost are same like traditional photogrammetry, and also the processing principle are almost same. Okay, UV photogrammetry is new photogrammetric measuring platform which operate remotely controlled autonomously without a pilot sitting in the vehicle. So that's all. Okay. Okay, I hope you understood the concept of photogrammetry. Okay, so in order to, as I said, in order to do 3D mapping, we need to have at least two images of the same object. We can see here, here is the left photograph, left image, and this is the right image. And this area which is highlighted here, uh, the same area covered by the second photograph. Okay, so same area you can see covered by the second photographs. So we call this area as an overlap area. Okay. Okay, so when taking the photograph, you have to consider overlap between your photographs. So that is most important thing when working with photogrammetry. Okay, yeah. And then basically, if you can see the same objects in the two camera station or two photographs, so these two are the same point within this within the overlapping area of these two photographs. So then we can use some mathematical model to do the 3D reconstructions based on the photogrammetric principle. So this is basically what we are trying to do in photogrammetry for 3D mapping. Okay, we should have overlap between photograph. Within this overlap, we can select common points, and then based on this common point, you can generate lines, and intersecting this line, you can compute a 3D location of image points. So that's all about these things. Okay. Okay. You can see here now the way how to collect your photographs. We have an aerial flight here, and we collect some photograph images with overlap in both directions. The overlap between two photographs along a flight line is called front overlaps, or the overlap between two photographs perpendicular to the flight direction we call the side overlap. Okay, so considering overlap between two photographs and between flight line, we can collect data covering your project area. And then you can use the photogrammetry techniques as I explain you in order to compute the 3D location by connecting bundle of the rays coming from the same features available within the consecutive photographs. Okay, so then you can generate a nice 3D outputs. As you can see here, you can generate a digital surface model based on these points generated through these photographs. Okay, in UAV photogrammetry, we can do the same things. We can collect a photograph having enough overlaps, moving the UAV along the flight line, as you can see here. Considering overlap between photograph, you can collect covering the your project area. Okay, then based on the same concept that I explained, we can process these photographs. Of course, we will explain the processing step later in detail, but in principle, we can use that photogrammetric principle to get the 3D location. Okay, if you go to the traditional photogrammetry with a high quality camera, we know everything about the camera, such as camera model, focal length, a principal point, orientation, and etc. We can control flying height and capture photograph by looking directly down, that is vertical photograph actually. All of this in traditional photogrammetry is very controlled situation because we know so much thing and we only need to tie these photographs together making measurements. It requires few parameters and thus requires only a few tie points per image. Traditional photogrammetry really control as we know a lot. Okay, so moving from that to modern photogrammetry, which use structure from motion techniques. techniques. As long as object has look from a multiple viewpoint in many overlapping images, we can automatically generate massive number of type points. Okay, so we do not need to know camera locations, and it is also not necessary to know how far it is. It is an automated technique evolved from machine vision, and it requires only massive number of points, which require a lot of image overlaps also. We can reconstruct the camera model from this imagery alone without having additional information like what we did in traditional photography. So that is the important thing when we working with the modern photogrammetry. Okay, so you can see in this picture actually, uh, we have taken photographs from multiple viewpoints to complete this object. So maybe you can see there is overlap between these two photographs. So this common point you can see from this camera location, or you can see this point in this camera location, and sometimes this point also will appear in this camera location. So there are a lot of photographs having same point. Okay, so you have lot of tie points. I will explain what does mean in tie point later. You have lot of common point. You can extract lot of common point based on these photographs. Okay, so these common point then you can use to generate 3D models. Okay, so that is the difference between traditional photogrammetry and the modern photogrammetry. Okay. Okay, so this is the model that generated based on this photograph. Actually, you can see there are thousands of photographs have been taken by covering this model, and you can see a very nice 3D model generated from these photographs. Okay. Okay, so let's talk about the mission planning then. A mission is the flight, drone flight, and the plan is the all thing we have to do. For example, checking weather, scheduling flight path, gathering equipment, checking batteries, planes, and extra things. So mission planning is the process what we do to achieve our goal. Why mission planning is important? So this is a great question, actually. There are a couple of reasons. Number one, you can obtain better data. We know that highly accurate line work and photogrammetry deliverables are dependent on the better input data. So the ultimate success of a project depends upon good quality photographs. Okay. The second reason is replicate missions. Of course, especially this is helpful with time series analysis. Then number three for mission planning is it is automated process. Also, we need care about mission planning because we can save time by selecting fewer ground control points, less ground surveying, shorter flight lines. Also, we can save office time because shorter processing time, better accuracy, fewer photogrammetric errors, simple drafting workflow, and many more things. Also, we know a lot of problems are caused by poor mission planning. Okay, yeah. The photogrammic missions must then be carefully planned and executed according to the flight plan for obtaining the required accuracy and completeness of the project. Failure to obtain satisfactory photography during a flight mission or to create the right flight plan is not only an economical loss in terms of time and resources, but also in all probability will cause to damage the UAV as well. I will show you some examples to show what happened when you did not consider it and if you plan your mission is wrong way. Okay, so you can see it here. Most of drone, for example, DJ Phantoms or some Chinese drones, fly mission in a single plane. and do not automatically adjust their flying height to the terrain characteristics. So you can see you can see here. Yeah, you can see it here. This can result in an insufficient image overlap, maybe less than 50% of overlap or less than zero, sometimes zero actually, when capturing higher terrain points, high buildings, high trees, etc. in case you start the mission from lower positions. Okay, so in this example, you can see the mission plan has been started from the lower positions, having 80% of overlaps. And when it goes to the higher positions, you can see this has been reduced to 50% overlap. Okay, this is because it changed the flying height. When it changed the flying height, uh, then overlap also is changed. Okay, uh, it's also changed. Okay, so start your mission from the highest point in the elevation to the terrain you are about to map. Okay, so that is the that's way you can solve that problem. Okay, so here you can see what happened if you change your starting point to these locations with the 80% overlap. When it come to these locations, you can see the overlap is increased to 90% percentage. It increased, but it does not matter because you have enough overlap. You can get a common detail based on this overlap area. Uh, of course, there are some problems also having this high overlap, battery problems, and it takes too much time. But we have data, we will not lose some of informations. Okay, so you have to take some of precautions based on your terrain type. Okay, that's what I want to tell you. We have to carefully plan your missions. So you should check all other important things. For example, if they are in an open area to take off landing. Especially, it is very important if you are using fixed wing drone because fixed wing drone need at least minimum 100 feet area to launch. And also fixed wing cannot avoid obstacle in their path. Okay, other thing you should check that is this a good project for drone photogrammetry, because a very large project having more than 500 acres uh, or 1 lakh of photograph, dense vegetation and tree covers underneath the trees are not suitable and considered as bad project for drone survey. Okay. Okay, so now talk about some of key inputs into a mission plan. So things to consider when planning out of measure include things thinking about the project goals. These things we can divide it into three groups. First one is flight parameters. So here you can select an area of interest, camera information, and what is the GSD that you want to select, and what is the height that you want to use to take photograph, and which overlap you want to apply, and these things you can consider during the flight parameter selection process. Second thing is the specification. Here you need to consider logistic and constraints such as time available for field, flight time, number of batteries, wind and weather condition, sun or how to avoid shadow problems, data processing resources, and etc. It is a good site, and also this is the good area for drone survey. Is it legal to fly here? And these things you can consider under specifications. Okay. The third group is available devices. Here you can think how many ground control points should I set, where should I set the ground control point, how should I arrange the flight plan, or pattern, what is the flight pattern, what data still need to be ground surveyed, which sensor and platform is suitable for this mission. This thing also you can consider, and you should select based on your project goal and the accuracy that you require. Okay. Yeah. At the end, so you can generate your mission plan and execute it. Okay, and now I will explain the way of selecting and computing some of these important parameters which need to be taken into account during mission planning. So let us start. Sorry. Okay, so let us start with the GSD, ground sample distance. Yeah. GSD, sometimes we call ground sample distance, is one of the most important variable that is used to understand the accuracy of an image. What does mean of survey accuracy? There are two types of survey accuracies, relative and absolute accuracy. Relative or local accuracy is the extent to which a given point on a map is accurate relative to the another point within that same map. Whereas absolute or global accuracy is the extent to which a point on a map corresponding to a fixed coordinate system in the real world. Example of relative accuracy: if the distance between 2 points is 2 meters in the real world, it should be also measured 2 meters on your map. On the other hand, if a map has global accuracy, the latitude and longitude of a point on that map should correspond accurately with actual ground coordinate, worldwide ground coordinate system. So how relatively accurate is your drone survey? And what does depend on? One of the main factors that determine the accuracy is the ground sampling distance. As you can see here in this picture, GSD is the actual ground distance between two consecutive pixel centers measured on the graph. The selection is actually depend on the size of the smallest object that the user like to see on the final image. The bigger the value of the image GSD means the lower the spatial resolution of the image and less visible details. Okay, this will also reduce the relative accuracy of measurements. You can see it here. This image has a bigger value, 25 centimeter GSD. So you can see less visible details. Okay. Smaller GSD, as you can see in this example, smaller GSD means more detail, but can introduce a lot of problems with classification and processing. For example, if you fly with the GSD of 1 centimeter instead of 3 centimeter, you are capturing and storing up to 10 times more data for the same area covered. So plan your GSD for purpose. Okay. Yeah. This is the general formula to calculate GSD. Actually, this is very simple formula, so that's why I put it here. So you can see here GSD depend on camera parameters, that is focal length and also pixel size and flying height. Okay. So remember then the GSD is related to the flying height. The higher the altitude of the flight, the bigger the GSD value. Okay, and vice versa. As a rule, the horizontal relative accuracy is 2 times the GSD, and the vertical relative accuracy is 3 times the GSD. For example, a GST 3 centimeter per pixel, horizontal relative accuracy is 6 centimeter, and vertical relative accuracy is 9 centimeter. But remember, it is all about trade-off. Okay, the project target relative accuracy needs to be chosen depending on the project accuracy requirement. So when selecting the GST, try to first access what type of accuracy you need and to what extent. This will help you determine how to go about the planning the flight and processing the imageries. If you think that you need global accuracy, a GPS are the most definitely needed for such kind of surveys. To make sure you understand the project requirement well enough to know whether you need ground control points or not. Because using ground control point, it will increase time spent on site and during processing. It is also increase your cost. Okay. Okay. Uh, to to obtain highest amount of global accuracy in any drone mapping project, most common and effective method is to use GPS. Accurate ground control will help you get better absolute accuracy. Ground control points are required as they can enhance the positioning and accuracy of the mapping output. So let's first talk what GPS are. Ground control points or GCPS are marked point on the ground that has a known geographic location. This means that each point will have 2D or 3D coordinate assigned to it depending on how you captured the point. The accuracy of the captured point can be as good as in the range of millimeter to as way of as 1 meter, a few meter. Again, it is depending on what instrument you use to capture the point. Ground control point can be anything that can be easily recognized in the image. So you can see two examples here. They are the ground control points. Ground control points. Uh, they can be anything, but make sure that they are unobstructed and clearly visible in images. Okay, that's all. Okay. In general, the ground control points are phased homogeneously, that is distributed evenly through the study area, not clustered. But a point can be placed in the middle of your or center of your project area for further increase in the quality of the output result. Here you can see the ideal layout for ground control point distribution. One ground control point at each corner and one in the center. Okay, minimum 3 ground control points are essential for processing photograph, but recommended one is minimum 5 ground control points. Of course, you can, for best practice, you can use 5 to 10 ground control points. If the area quite large, large, or as well as for more complex areas, you can use more than that. Okay, if the terrain is undulated, more ground control points are needed to be distributed among the undulated terrain. So you can place ground control point across the different elevation, as you can see this example at the top and bottom of a hill as example. Okay, adding more ground control points will not make a significant change in the final accuracy. So quantity, quality, and distribution are all important factors to consider when selecting ground control points. Okay, not just increasing the number of control points. Okay. Okay. The next thing is overlaps. As I said to you, everything we are going to do with UAV imagery is based on overlaps. Overlap means we can see the same features in multiple images and can generate tie or key point between these areas. So I already explained explain that there are two different type of overlap we have to consider when collecting the photograph: overlap between consecutive photographs and overlap between two flight lines. Okay, so if you have a smaller overlap between two photographs, as you can in this picture, you will get few tie points, so less than 100 points. Okay, having 20% overlap. If you have a bigger overlap, so you will get massive number of tie points, so more than 1,000 points. In general, to generate 3D models from images, it requires a massive number of tie points. It requires 1,000 match point per pair of photographs. The minimum overlap, frontal overlap is 75%, and we can go to 90% also. The minimum side overlap is 60%. But this depend on the area also. If you are work with vegetation area and topology having deviation changes, then you have to change this minimum requirements. Okay. Okay, so based on that overlap, you can generate a flight map. You can see an example. Example is here. So these circles indicate camera location or photo locations. Okay, yeah. As I said to you, this depends on the image size, visual contents. For example, for agriculture and dense vegetation area, you should increase the overlap. Maybe you can use frontal overlap as 85%, and side overlap, maybe you can use 80% to obtain enough tie points. Okay. Okay, but topography, that is large elevation changes, can impact on overlaps if flying at one height, as you see here. Okay, so this already I explained. What happened if you use a same height, one plane when collecting the data. What happened to this overlap? We change the elevation of the area. Okay, so as you can see on the right of the image, here there is a higher overlap between photograph on the lower section of the terrain. But as we go to the left, we end up with smaller overlaps or no overlap between photographs sometimes. It depends on the flying height. Okay, because if you go to this area from here to there, you can see the height is reduced. Because of that, overlap also is reduced in this area. Okay, so what are the solutions for this type of problems? Images without overlap pose serious issues for photogrammetry and can make part of your survey unusable. Also, ground sample distance will increase if you start flying over higher ground and move to the lower ground. Okay, if you started from this location, so the ground sample distance is quite larger here than in this area. Okay, thus reducing the detail and accuracy of your survey. So you can run then multiple patterns at different altitudes as seen in this figure, or fly to follow the terrain. Also, it is one option to avoid this type of problems. Okay, in most of the current UAV system, you have this capability to fly along the terrain, following the terrain changes. Okay. Okay, so the next thing that you want to think is the flight plan types. So there are different flight plan types for different needs. You can see here You can see here, but this option can change based on the flight plan in software. There are 5 different missions come with a fixed 4D capture software, as you can see here. The first one is a really quick method and depending on the height and size of your area, and it used for 2D maps. If you want more detailed 3D map, you can use a double grid method at the same altitude. Double grid will take longer, so it needs more batteries, but provide more detail. Polygon type flight plans allow you to have more control over the shape of the flight plan and make 2D map as well. The next one is the circular pattern type. The circular pattern helps to create 3D models of single object, for example, archaeological monuments. In general, it is recommended acquiring images using regular grid pattern, as this allows an easier identifications of the common point among the images during the processing. Okay. Okay, then what happened if the area is quite large? And if the area quite large and not possible to cover by one mission plan, then what we can do? Then you can use multiplied missions. However, you need to consider proper overlap between these missions plan. For example, the third picture has poor overlap between these two mission plans. Okay. And the second picture demonstrates two flight paths with enough overlap between these two plans. In the first one, you can see there is a repeat flight line to make uh, enough overlap between these two flight paths. Okay. Yeah. However, the different plans are taken as much as possible with the same line height, as two different heights lead to change in spatial resolution. Okay. Okay. Yeah. Finally, now with the knowledge of the area of interest and the parameter that you already selected, can generate it. That you can generate it your flight map. Okay, so you can see it here. Based on the parameter that you already computed, you can adjust these values here, and then based on that parameters, you can see it is automatically calculate flight lines, image position to be taken photograph in this way. Okay, then after completing this process, you can start your mission plan. So you can see here the person who is controlling this process, and then the UAV system collecting photograph by moving along the flight path that you already generated is here. Okay, so you have to you should consider. So there's some. Please give me 1 minute. Okay. Yeah. So this is the next one. Okay. So now with the knowledge, as I said, we already obtained during the mission planning. So you can generate this one, and then you can execute your flight missions, as you can see it here automatically. automatically. So you can see start points and end point. Instead of start and end point, of course, you can include point called home points for safety reason. For example, if the mission fails, the UAV mission fails, the UAV has to go to the nearest home point that you assign. Okay. There are various advanced tools in most of today UAV navigation software. They also reduce human invention and safely navigate your UAVs. Okay, so if you look up the drone capability today, the drone are many flight mode. For example, you can fly them in highly manually, that is manual mode. There are other modes also like fly by wire that reduce rolling effect in left right direction, so it will maintain the stability of the flight. Fully autonomous flight mode also you can use, or auto landing option also you can use, so you do not worry about the landing process. Drone can hold the altitude by altitude hold options. So there are very high level commands available in today UAV system. Also, drone have a fail shape option. For example, if the ground control station is failed or no radio or GPS connection, you can ask drone to about the mission and come back to home. Uh, that is a good advantage. That is a advantage also. There is another new option called collision avoidance. This has been adopted to most of the current drone, for example, sonar, IR, LiDAR sensors to see obstacles. Okay, so then we can stop. If there is obstacle, we can say stop your mission and come back to the nearest home point, something like that. Okay, and also you have to think something more about some more thing when generating this flight line. If you want to have fewer flight lines, so you can increase the flying height, or if you want to reduce the shadow problem, so you have to think about the solar directions, solar positions, wind directions, and many more things you have to also consider during this mission planning process. Okay. Okay, here you can see some of selected mission planning software's applications. So you can customize your drone mission plan easily using these different type of applications or softwares. Okay. Okay, all right. So the next step, next topic is the processing this drone data. There are various software today available for processing drone data. For example, Fix4D, Exop, ArcGIS Pro with CDM, and etc. However, they all have some generic steps that we are going to talk here. Okay, drone images are also processed using the same techniques of photogrammetry. The processing scheme is then broadly divided into several sections, as you can see in this flow chart. Actually, what they are then, but the first step is the key point extraction, and the second step is the image matching. The next step is the block adjustment, photogrammetric processing step, including camera model calibration, aerial triangulation with a bundle block adjustment. Then you can generate a sparse point cloud, and based on this point cloud, you can generate all the deliverables that we are expected. Okay. Let's talk about these major steps in detail. The first one is key point extraction. That is creating massive number of key points. What does mean key points? Key points are spatial location or point in the image that are interesting in the other image. Or we can say it as more unique features which differentiate from other features easily. They are interesting because no matter how the image changes, you should be able to find the same point in each image. So you can see in this example, these are very very remarkable features. Even your second image change with scale, rotation, transformation. So this type of feature will not change in that image, in the second image. So we call this point as interesting point. Okay, it will not change with the rotation or scale changes, transformation, or partially with the illuminance. Okay. Okay, key point from each image can be extracted. So there are a number of automatic computer vision algorithms for extraction of key point. The common techniques for extracting key point is the scale invariant feature transformation algorithm. So this indicate features in an image scale space that are invariant to image transformation, as I said, scaling, rotation, and partially invariant to illumination changes. A key point detection become more problematic in areas of low texture variation, such as dense forest, water, sky, and so on. So this is the example, two example of extracting key point. Okay. Okay, so then the next step is type point extraction, or we call this image matching process. When all the features, that is key point, have been extracted, the corresponding features in multiple images need to be searched. So what does mean corresponding point? So let's assume this is the point that you want to search in the second photographs to know of, by looking here. You can see the same point. This is the same point. So we can say this is the corresponding point to this point. Okay. So in the third photograph, you can see the same point. So this is the corresponding point, this one. Okay. So look. So during image matching process, we are looking corresponding point or similar points. Okay. So sometimes we call this corresponding matching problem or image matching problems. Okay. Yeah. So yeah. Image matching, that is used to identify and uniquely match corresponding key points that are located in the overlapping areas of all nearby images. The match point we call as tie point. There are various image matching methods. Feature-based matching is often applied in many tasks. Okay, so keep in mind, all key points are not equal to tie point. We use key point, and the only match point we consider as tie point for the processing. Okay. Because sometimes this point will not appear in the second photograph. So then you will not get the matching point for that one due to the obstacles or illumination problem. There are various reasons will not appear same point in the other photograph. So if we can't obtain matching point for this one, so that meaning this is the key point and not a tie points. Okay, only match point we consider as key points. Okay, so you can see nice output is here, or the match point based on the any feature matching software we can use to get this result. Okay. Okay, so then we can reconstruct. We can start the reconstruction process. After determining the coordinate of the same point in two images of an object, the 3D position of that point can be calculated using knowledge of camera data and also the relative orientation process. You know, every image generates a bundle of the rays, as you can see in this picture. All these bundle of rays from multiple images intersect to create a dense network. So we call this as bundle box adjustment. Okay. Using this method, all photographs can be simultaneously adjusted or oriented, and then XYZ object coordinate of all the measured tie point can then be computed. Based on this tie point, we can have then a sparse point count, as you can see here. Okay. Yeah. Using yeah. using the dense image matching method, a dense point cloud also we can generate it. In order to generate a dense point cloud, a corresponding point is required for almost every pixel in the drawn image. So then this dense point cloud can be colorized by color extracted from RGB value of images. Or you can generate this dense point cloud based on the sparse point cloud that you already generated by applying any interpolated or extrapolated method. Okay. If you're interesting to see a 3D mesh model, you can generate it from this dense point cloud by triangulating these points and making a network of triangle. Actually, I explained this very briefly, but this is quite a complicated process. Okay, it's simply if I say this, a mesh model is model that is generated by connecting these dense point cloud and making network of triangles. Okay. Okay, so then you can generate mesh model and overlay. You can overlay this mesh model with the photograph or the photos actually in order to get the 3D model. Okay. Okay, the next step is the generation of other deliverables using this dense point cloud. Once a dense point cloud is generated, they are triangulated to create digital surface model. If you are interested to have a DTM, so this is the digital terrain model. Easily you can generate this based on the detected dense point cloud directly. If you want to generate a digital terrain model, so first you need to classify this dense point cloud, and you should remove all object point. Okay, then only the ground point you can use to generate this digital terrain model. Okay, so then of course you can apply some smoothing tools to smooth your surface in order to make good visual contrast. Okay. The next one is orthophoto. Next output is the orthophoto, and orthophoto is an image that has been geometrically corrected. We call this is the auto-rectification process. The auto-rectification process of each image is completed using the digital surface model that you already generated based on the dense point cloud. And point cloud. So as this is already geometrically corrected, you can use it as a map to get the measurements easily, and you have a lot of detail compared with the vector map. Once all photograph or the photos are generated, so these individual orthophotos you can join, we call mosaic, together to generate a large ortho maps. Okay. And of course, then this output you can use to generate contour maps and 3D model as well. Okay. Okay, now let's see accuracy of drone survey. Accuracy of a drone survey. What are the methods to ensure drone survey accuracy? How to improve precision in UAV mapping? The new technology, that is structure from motion, can produce very internally consistent result without GPS or ground control points. Type points created from a lot of image overlap, image overlap can make everything fit together quite well with no position information, whatever. Okay, but if we want to repeatability for change detection or to compare your result to those collected from another survey via drone or other methods, we want to georeference your imagery and surface model to real world coordinates with high confidence. So there are the example also. So I'm not going to tell all those things. So doing so requires some extra effort. Okay, so let's talk the various method and technology that make for an accurate drone survey. The first option is ground control points. We already discussed about the ground control point, how to distribute your ground control point, what is the minimum requirement, how it should be appear in the area, what else? Okay, these things. Okay, so the technology is very simple, well understood, and widely used method. However, significant amount of time is required to set up ground control point, depending on terrain and the size of the study area. It can take much longer to perform a drone survey with ground control point than with other methods due to the complex setup. In difficult terrain, it may not be possible to safely or easily set up ground control point also. Okay, uh, so there are advantage and also disadvantage. That is normal. Okay. Okay, relatively new advances with drone technology, specifically their integration with GNNS technology. We can use real-time kinetic and post-processing kinetic method in order to increase the accuracy of our uh, outputs. Okay, uh, so actually this method can make the process easier, safe, and less consuming when compared with the normal ground control setup process. Real-time kinetic is a technique used to enhance the precision of position data derived from a satellite-based positioning system. I hope you know everything about this method as well. So which relies on a single reference station or interpolated virtual station to correct your tag location while in flight. Okay, in other words, RTK is the correction method that enhances GNNS precision. To use RTK applied in open terrain, and within 2 or 3 kilometers of the ground station is ideal. Okay, uh, the here you can see we do not need to use post-processing step because during the data acquisition process you can apply correction uh, for your data. Okay. The next one is post-processing kinetic methods. Actually, this is almost same to the real-time kinetic process without having post-processing step. Okay, so this is yeah. Basically, the main difference between the two is when this positional correcting take place. RTK correct position during the flight and PPK uh, uh, correct position after flights. Okay, so it has post position step 2. Okay. However, accuracy of any drone survey will change based on the various other factors too. Not only these things, as I said earlier, even though you use ground control points, most accurate ground control point, sometimes you cannot obtain the required accuracy because it depends on the distribution of your point, number of point, and the accuracy of that available ground control point, which instrument you use to establish those points, and so many things. Okay. Okay, so that's all about the UV mapping, 3D mapping with UAV. Here I gave you a very brief introduction to 3D mapping with UAV technology. I know there are a lot of things to we have to explain. There are a lot of theoretical thing behind that one, but just I give you a very brief. I introduced very briefly all those steps that are necessary to complete any drone survey. Okay, thank you very much for all of you. Hello.
Thank you very much, madam. So thank you very much, today's guest speaker, Dr. Nalani Hettiarashige, for dedicating your valuable time for us. So I believe that it was really an informative, effective, and productive session. So, madam, on behalf of all the participants, I really appreciate this precious session, and I'm very much grateful for all the participants for their attendance today. So hopefully we will meet with another interesting and valuable session like this in near future. And until then, stay safe and goodbye.
Okay, thank you very much for you also and all the participants in this session. Yeah, so if you have, we can meet again. If you have any problems, you can also discuss, or if not, we can close this session. Okay, so we can stop, I think. Thank you very much again, all of you.